Section 11.1a is about square roots or radical expressions, and we're going to talk about the product property of square roots when you multiply things that involve square roots. Now, a radical expression is an expression that contains a square root. Square root symbol looks like this. We've used that in the past. And now we'll say that the expression under the radical sign, so the stuff that's going to be under that sign, is called the radicand. And to be in simplest form, the radicand, or the numbers and letters underneath there, must contain no perfect square factors. Now, what does that mean? It means something like the square root of 5 is okay. It's the simplest form because the number 5 has no perfect square factors that make it up. But something like square root of 20, the number 20 has a perfect square as one of its factors. 4 is a perfect square, and 4 times 5 are both factors of 20. So we would say that something in this form is not in simplest form because it contains a perfect square factor. Now, there is a property called the product property of square roots that helps us deal with simplifying these radical expressions. And what it says is that if you multiply two numbers and they're underneath a radical, you can break that up into two separate square roots. And so this is the way that we're able to take out factors that are perfect squares out of a square root. So let's see how it works. If I want to simplify the square root of 12, my goal is to find a factor of 12 that is a perfect square. Now I'm just going to list all the factors of 12 just so you see them. This is not something that you have to do in every problem, but these are all the factors of 12. These are all the numbers that multiply to give us 12. If you notice, there's one of those numbers that's a perfect square, and it's that one right there. And it's that number that we want to use to break up 12. So according to this property, if I can do the square root of 12, I can do the square root of 4 times 3. I can break it up. And then, according to the property, I can make that the square root of 4 times the square root of 3. Now, why is that beneficial? Because whenever you have a perfect square, like the number 4, and you take its square root, it's easy to find the answer, the value. The square root of 4 is 2, because 2 times 2 is 4. And so now this is what the simplified answer for the square root of 12 would be. Pull out a perfect square, take its square root, and simplify the expression. Our next example is the square root of 90. So we have to think about any factors that exist in 90 that are perfect squares. Well, I know of 9. 9 times 10. So according to the product property, I can make this the square root of 9 times the square root of 10. And what is the square root of 9? It's 3. So 3 root 10 is how we would simplify the square root of 90. The key here is picking factors that are perfect squares. The number 4 here is a perfect square, which is why we picked it. The number 9 here is a perfect square. That's why we picked it. You want to pick a factor that's a perfect square. If you don't, then breaking them up like this won't do any good. Here are some more examples using the square root property. Again, I want to find a perfect square that exists in 72. So I'm going to list all the factors of 72. So these are all the factor pairs, and we're looking for perfect squares. Are any of those numbers a perfect square? And the answer would be 9. So I can break up square root of 72 into 9 times 8, and according to the square root, or the product property of square roots, I can make that square root of 9 times the square root of 8. And the square root of 9 is just 3. So this becomes 3 square root of 8. Now there is another number still that's a perfect square of 8. So I could break up 8 into 4 times 2, and then break this up into square root of 4 times the square root of 2. And what is the square root of 4? Well, it's just a 2. And then finally, 3 times 2 is 6, so 6 root 2 is your answer. Now, that's actually pulling out two perfect squares. We pulled out a perfect square here, square root of 9, and we pulled out a perfect square here, square root of 4. Now, if you would have noticed something about all of these factors, 36 is also a perfect square, and 36 is bigger than 9. So if we were clever about this, we could have broken this up into square root of 36 times 2, and the square root of 36 is just a 6. So we would have ended up with 6 root 2 anyway. The reason I show that to you is because you want to try to pick the biggest perfect square out of a number. In this case, 36 would have saved you some work. But if you don't pick the biggest perfect square, you still can get the final answer by pulling out a perfect square multiple times. Our next example has no perfect squares in either of those numbers. So what I'm going to do is I'm going to take the square root of 3 times the square root of 15 and put it together and make it the square root of 45. Now why that's useful now is there is a perfect square in 45. And the answer is 9. So root 9 times root 5 becomes 3 root 5. Here's another example using the product property. The property also works in reverse, so root 2 times root 24 becomes a root 48. So my goal is to try to find a perfect square in 48. Well, 48 is 16 times 3. And since 16 is a perfect square, I could make it the square root of 16 times the square root of 3. And the square root of 16 is 4. Now, to me, that's the easiest way to do it because 16 is the biggest perfect square. If you didn't recognize that, you could have taken square root of 48 and broke it up by dividing it by 4 and making this square root of 4 times the square root of 12. Square root of 4 is 2, but you'd also have to recognize that there's another perfect square factor inside of 12. You'd have to recognize that this would be square root of 4 times the square root of 3. And the square root of 4 again is 2, and then we can multiply 2 times 2, but we get the square root of, or we get 4 square root of 3 anyway. Now, very briefly, I want to remind you about these numbers that we've learned in the past that are called perfect squares. Those are the numbers that are created by squaring something. So the numbers that you see here, 1, 4, all the way down to 100 here, these are perfect squares, and they go on. 11 squared is 121, 12 squared is 144. They go on forever. But those perfect squares are the numbers that we're looking for that exist as factors underneath a radical sign. Those are the key numbers that we're trying to find when we're simplifying these radicals. Now I'd like to look at how to simplify variables with exponents. If you remember in the past, we've talked about how squares and square roots are enemies of each other, and they undo each other. So taking the square root of a square really just leaves you the base that you had there. So square root of x squared is just x. But if you think about it, what numbers could you plug into x here to square something? Well, if you had something that was squared, that number could be positive or negative, and it would still make it work. So to account for that situation, we have to include this absolute value sign. And when you take the square root of an even exponent, your solution needs to have an absolute value on it. I'm going to show you a little bit when to use that coming up here. So we say that the square root of x squared is the absolute value of x. To be honest, I don't always use the absolute value. It's the official answer, and I'm going to show it to you now, but a lot of mathematicians just use x and move on with life, so I'm really not going to mind if you do that. But let's examine square root of x to the third. By taking x squared and removing a single x, or by taking x cubed and removing a single x from it. And now we have the square root of x squared, which we know up here is just x. And then we have this little square root of x thrown in the back. So what's happening here is you're taking the square root of an even exponent, you're just simply cutting the exponent in half. So let's look at x to the fourth. That's the same as x squared squared. When you take the square root and you cancel one of those squares, you end up with an x squared. So notice again what happened. You have an even exponent. All you have to do is cut that exponent in half, and you can remove the square root. How about x to the fifth? Well, that's the same as square root of x to the fourth times the square root of x. And we already know what the square root of x to the fourth is. It's x squared times the square root of x. So hopefully you're starting to see the pattern. When the exponent's even, you cut it in half. When the exponent's odd, you take a single square root of x out, cut the new even exponent in half, and write it that way. So x to the sixth becomes x to the third squared, which ends up being x to the third. Now back to what I originally said. Whenever you have an even exponent that ends up being odd, like this one and this one, you need to include an absolute value as your answer. So the red stars here really talk about this note. When radical expressions contain even exponents and it's simplified to an odd, you must use an absolute value to ensure non-negative results. So here's some examples using variables. I find this easiest to break it up into separate square roots using each letter. So square root of 45, we're looking for a perfect square in there. I see a 9 and a 5. Square root of 9 is 3, so we'll reduce that as 3 root 5. Square root of a to the 4th, we know that we're going to cut the exponent in half and make it an a squared. Here, we're going to have a b to the 4th times the square root of b, because remember we said we're going to pull a single square root out and then make this b squared, cut it in half, and then we have the extra square root of b on the back. And then the last one is square root of c to the 6th. All you do is you cut the exponent in half. Now technically, because we had an even one that's simplified to an odd, we should include absolute values, and the book will have that as a solution, but I'm not going to include that here. When you write the final answer, you take everything that's outside of the square root or outside of the radical sign, that goes in front, and then everything inside the radical sign goes in the back underneath it. Our second one we will break up again. I just think it's easiest to do that, and you can take every letter individually. So what perfect square is in 40? How about a 4 times 10? Square root of 4 times square root of 10 is 2 root 10. For the x, it's got an even exponent, so we cut it in half. For the y, we make it y to the 4th times the square root of y, and that becomes y squared times the square root of y. And then for the z, square root of z squared times the square root of z, and that becomes a z with a square root behind it. Writing everything outside of the radical sign first, and then everything under the radical sign comes at the end.